Hello and welcome everyone. This is Gursimran Singh. In this session, we will discuss classical cryptographic techniques that are substitution ciphers, mono, polyalphabetic and polygram substitution. Cryptography, that is science of writing the secret text, is not a new science. The first known evidence of the use of the cryptography in any form or in some of the form was found in around 1900 before Christ in Egypt. Cryptography recorded the remarkable growth with the development of Rotor and Enigma machines around the world wars. In early 1970s, the Big Blues from America, that is IBM, founded the crypto group. In 1990s, DES, that is Digital Encryption Standard, was developed, and then RSA and AES were developed. In modern times, we have so many strong cryptography mechanisms. Future is of elliptic curve cryptography and quantum computation cryptography. So, the main objective of this lecture is to discuss the substitution cipher techniques with their pros and cons. So, let us start our discussion with classical and one of the oldest cryptography technique, substitution ciphers, which is symmetric in nature. But before discussing the substitution cipher, let us have a look at symmetric cipher model. A symmetric encryption scheme has 5 main components, that are plain text, that is the original understandable message or data that is fed into the algorithm as a input. So, the second is encryption algorithm. The encryption algorithm performs various substitutions and transformation on the plain text. The third one is secret key. The secret key is also input to the encryption algorithm. The key is the value independent of plain text and of the algorithm. The algorithm will produce a different output depending upon the specific key being used at the time. The exact substitution and transformation performed by the algorithm depend on the key. The fourth one is ciphertext. This is the scrambled message produced as output. It depends on the plain text and secret key. For a given message, two different keys will produce two different ciphertexts. The ciphertext is an apparently random stream of data and as it stands is untangible. The fifth one is decryption algorithm, and that is the most important aspect. This is essentially the encryption algorithm run in reverse. It takes the ciphertext and the secret key and produces the original plain text. Now, in this figure, we represent the concept of the symmetric cipher model. So, in this model, plain text is used as input. We convert the plain text into ciphertext by using encryption algorithm and key. On the receiver side, ciphertext is converted into plain text by using a decryption algorithm and the key. Sender and receiver share the same secret key. There are two requirements for secure use of the conventional encryption. The first one is we need a strong encryption algorithm. This requirement is usually stated in a stronger form. The opponent should be unable to decrypt the ciphertext or discover the key, even if or she is in possession of number of ciphertexts together with the plain text that produced each ciphertext. And the second point is sender and receiver must have obtained copies of the secret key in a secure fashion and must keep the key secure. If someone can discover the key and knows the algorithm, all communication using this key is readable. On the sender side, with the message P, that is plain text, and the encryption key K as input, the encryption algorithm forms the ciphertext C. We can write this as, that is, ciphertext is equal to the encryption function of the key and the plain text, where P is equal to plain text, K is equal to key, and C is equal to the ciphertext. On the receiver side, decryption can be performed as decryption function of key and ciphertext. Now again, where P is equal to plain text, K refers to key, and C refers to the ciphertext. Now in substitution techniques, letters of plain text are replaced by other letters. If the plain text is viewed as a sequence of bits, I mean 0 and 1, then substitution involves replacing plain text bit patterns with ciphertext bit patterns. It means 0 and 1 will be replaced with the 0 and 1 only. To write down a key for the substitution cipher, we first write down the alphabets and then a permutation of the alphabets directly under it. It means plain text will be written over, and under that we will write the ciphertext or the key. Obviously, the ciphertext will be computed from the combination of the plain text and the key. This mapping gives the substitution we make between the plain text and the ciphertext. Now plain text alphabets A, B, C, D and so on, and the ciphertext will be written exactly under this G, O, Y, D, S and so on. Now, so encryption involves replacing each letter in top row by its value in the bottom row. Decryption involves first looking for the letter in the bottom row and then seeing which letter in the top row maps to it. Hence, the plain text word hello would encrypt to the ciphertext as ESVVJ. If we use the substitution given above, the number of possible keys is equal to the total number of permutations on 26 letters. Substitution cipher can be of two types, that are monoalphabetic and polyalphabetic. If the substitution is done uniformly, this is called a monoalphabetical cipher or simple substitute cipher. In simple words, we can say in monoalphabetic substitution, an alphabet is replaced with the same alphabet in the entire text. So it means if you have replaced the A with the E, so each time in the entire text A will be replaced with the E. Now polyalphabetic substitution, different substitutions are made depending upon where in the plain text the symbol occurs. It means the same character can be replaced with different characters in the text. For example, A can be replaced with D and B in different places of the occurrence. Let us discuss some examples of monoalphabetic and polyalphabetic substitutions. First of all, we will discuss Caesar cipher, the earliest and simplest known monoalphabetical cipher. This can also be called shift cipher. The Caesar cipher involves replacing each letter of the alphabet with the letter standing 3 places further down in the alphabet. For example, now if your plain text is hello, that will be replaced with the 3 alphabets down, then the ciphertext will be KHOOR. Now note that the alphabet is wrapped around so that the letter following Z is A in a circular manner. We can define the transformation by listing all possibilities as in the plain text A, B, C, D and so on. In the ciphertext it will be D, E, F, G and so on. It means 2 places down. Now let us assign equivalent numbers to each of the alphabets. As you can observe in the table, we have written 0 for A, 1 for B and so on. Now, the Caesar cipher algorithm can be expressed as ciphertext equal to plain text plus 3 mod of 26. For each plain text letter P, substitute the ciphertext letter C. A shift or the key K may be of any amount, so that the general Caesar algorithm, it means we are not taking key as 3 now, we are not going 3 words down. Now, we can take key as any number. Ciphertext will be equal to plain text plus key mod of 26, where k can be taken in the range of 1 to 25. So, we have generalized the Caesar cipher. It means we will not be taking k 3 every time. We can take k in between 1 to 25. The decryption algorithm is simply plain text equal to ciphertext minus key mod 26. Now, if it is known that a given ciphertext is a Caesar cipher, then a brute force cryptanalysis can easily be performed. Simply, we need to try all the 25 possible keys. Now, let us have a look at implementation of Caesar cipher using a C programming language code. So, first of all, let us see the encryption function used to encrypt the plain text into ciphertext by using Caesar cipher technique. In this function, we use the integer p for plain text, c for ciphertext and key for shift or key that can be in the range of 1 to 25. Now, CHR set, that is char set, contains all the characters from A to Z. Now, C is equal to P plus key modulus 26 is used to encrypt the plain text. So, this is the main function to encrypt the plain text into the ciphertext. Now, let us have a look at decryption function also, that is used to obtain plain text from the ciphertext. So, encryption, we have converted the plain text into the ciphertext, and in decryption we will obtain the plain text from the ciphertext. Here P is equal to 26 plus C minus key modulus 26. This function is used to obtain the plain text from the ciphertext. Now, let us also have a look at how Caesar cipher can be cracked. The code to crack the Caesar cipher is, now in this code we are trying each and every possible combination of characters to crack the Caesar cipher. That means it is a brute force attack. I mean, if you are trying each and every possible computation, it means it is a brute force attack. Now, finally, let us put all the things together and run the complete code. Now, after compiling it, let us run it. Now, first of all, enter the string to encrypt. Now, let it be DOABA, DOABA. Now, enter the key, let it be 2. Now, you can observe the encrypted data as FQCDC. Now, we have defined the decrypted function also. You can see the decrypted data as DOABA again, and in Caesar attack you can observe all the combination of alphabet, and among them you can observe DOABA also, that is DOABA, that is our original text. Note that in this program we used only small alphabet for encryption, but the basic rule is the encryption will be done on the small alphabets and the ciphertext will be the capital alphabets. Now, let us discuss the second substitution technique, that is polyalphabetic substitution. Polyalphabetic technique have some features in common, that are: number 1, a set of related monoalphabetic substitution rules is used. Number 2, a key determines which particular rule is chosen from a given transformation. The best known and the one of the simplest such algorithm is referred to as the Wigner's cipher. In this scheme, the set of related monoalphabetic substitution rules consist of 26 Caesar ciphers with shifts of 0 through 25. It means there are 26 shifts. So, each cipher is denoted by a key letter, which is the ciphertext letter that substitutes for the plain text letter A. Thus, a Caesar cipher with a shift of 3 is denoted by the key value D. To aid in understanding the scheme and to aid in its use, a matrix known as the Wigner's table is constructed. Now, in this table, each of the 26 ciphers is laid out horizontally with the key letter for each cipher to its left. A normal alphabet for the plain text runs across the top. The process of encryption is simple. Given a key letter X and a plain text letter Y, the plain text letter is at the intersection of the row labeled X and the column labeled Y. In this case, the ciphertext is V. So, in the table, we need to select the key alphabet from the column on the leftmost part of the table, find plain text written on the top of the table, and intersected word of key and plain text is ciphertext. To encrypt a message, a key is needed that is as long as the message. So, it means the message and key will be of the equal length. Usually, the key is a repeating keyword. For example, if the keyword is deceptive, the message "we are discovered, save yourself" is encrypted as. Now, key is obviously the deceptive and we are repeating the key here. Now, the plain text is "we are discovered, save yourself." Now, the ciphertext that will be formed from the given key deceptive and the plain text will be Z, I, C, V, T, W, Q and so on. Now, decryption is equally simple. The key letter again identifies the row. The position of the ciphertext letter in the row determines the column and the plain text letter is at the top of the column. The strength of this cipher is that there are multiple ciphertext letters for each plain text letter, one for each unique letter of the keyword. Thus, the letter frequency information is disguised. However, not all knowledge of the plain text structure is lost. Let us compile this one out. Now, let us run it. Now, after running the program, first of all, you need to enter the plain text to be encrypted. Now, let it be again DOABA. Now, enter the key. Let the key be HELLO. Now, the encrypted text is KSLMO. Now, check this encryption with the Wigner's table. So, we have K for D, S for O, L for A, M for B and O for A again. Done. So, it is matching with the table and we are having different alphabets for every occurrence of the A alphabet. So, it is instructive to sketch a method of breaking this cipher because the method reveals some of the mathematical principles that applies in cryptanalysis. First, suppose that the opponent believes that the ciphertext was encrypted using either monoalphabetic substitution or a Wigner's cipher. A simple test can be made to make a determination. If a monoalphabetic substitution is used, then the statistical properties of ciphertext should be the same as that of the language of the plain text. So, there should be one cipher letter with relative frequency of occurrence. So, if only a single message is available for analysis, we would not expect an exact match of this small sample with the statistical profile of the plain text language. Nevertheless, if the correspondence is close, we can assume monoalphabetic substitution. Now, if on the other hand a Wigner's cipher is suspected, then progress depends on determining the length of the keyword. Now, let us concentrate on how the key length can be determined. It means how this algorithm, security algorithm, can be cracked. The important insight that leads to a solution is, if two identical sequences of plain text letters occur at a distance that is an integer multiple of the keyword length, they will generate identical ciphertext sequences. Now, for sure, an analyst looking at only the ciphertext would detect repeated sequences at a displacements of 9 and make the assumption that the keyword is either 3 or 9 letters in length. The appearance of same sequence twice could be by chance and not reflect identical plain text letters encrypted with the identical key letters. However, if the message is long enough, there will be a number of such repeated ciphertext sequences. By looking for common factors in the displacements of the various sequences, the analyst should be able to make a good guess of the keyword length. Now, the solution of the cipher now depends on an important insight. If the keyword length is n, then the cipher in effect consists of n monoalphabetic substitution ciphers. Now, let us consider an example. Suppose the keyword deceptive, the letters in position 1, 10 and 19 and so on are all encrypted with the same monoalphabetic cipher. Thus, we can use the known frequency characters of the plain text language to attack each of the monoalphabetic ciphers separately. The periodic nature of the keyword can be eliminated by using a non-repeating keyword that is as long as the message itself. Wigner's proposed what is referred to as an auto key system, in which a keyword is concatenated with the plain text itself to provide a running key. But surely, polyalphabetic substitution is far better than the monoalphabetic substitution. Now, let us discuss polygram substitution. Polygram substitution cipher involve group of characters being substituted by the other groups of the characters. Sequences of two plain text characters, bigrams, that is also known as bigrams, may be replaced by other bigrams. The same may be done with the sequences of three plain text characters. Now, three plain text characters are known as trigrams, 2 are known as bigrams and 3 are known as trigrams, or more generally using n-grams. In full bigram substitution over an alphabet of 26 characters, the key may be any of the 2's raised to power 26 bigrams arranged in the table with the row and column indices corresponding to the first and second characters in the bigram, and the table entries being the ciphertext bigram substituted for the plain text pairs. There are then 26 raised to power 2 modulus keys. The advantage of this is, first, the frequency distribution of digraphs is much flatter than that of individual letters, though not actually flat in real languages. For example, TH is much more common than XQ in English. Second, The larger number of symbols requires correspondingly more ciphertext to productively analyze later frequencies, because 26 raised to power 2 is equal to 676. To substitute pairs with the substitution alphabet would taken an alphabet 676 symbols long, which would be rather weighty. The example of polygram substitution is Playfair. We will discuss the Playfair in next lectures. To conclude, we can say the substitution techniques that are monoalphabetic, polyalphabetic and polygram substitution have their own pros and cons in practical implementation. We can say in monoalphabetic substitution techniques, the alphabet is replaced with the same alphabet throughout the text. That is why it is not very secure. The second technique discussed is more secure due to the occurrence of different alphabet for same alphabet in the text. So, that is it for today's session. Thank you for watching.